Hi, this is the lecture on Chapter 14, Acids and Bases. We should be a little bit familiar with acids and bases, even though we don't think about them in those terms, but at least with some of their characteristics, because we see them every day and we use them every day. But hopefully, at the end of this chapter, we'll understand a little more about some of these chemicals that we use and why are they acids and why are they bases and how they react with each other, and just so that we can understand a little bit more about these chemicals that we use in everyday life. First of all, let's classify them. Let's talk about what an acid is and what a base is, and just give some characteristics, general characteristics of what each of them are. Let's start with acids first. In general, acids will taste sour. We know this even though we don't think about it, but vinegar is a weak acid, and we know that vinegar tastes sour because we use it in our food and we have tasted it. We know that vinegar tastes sour. Lemons, for example, taste sour as well. They have citric acid, so they have an acid. They're weak acids, that's why we can eat them, but they taste sour in general. They can react with bases and neutralize them. So if I have, maybe you've seen these, the new craze is to come up with cleaning products that are not as harsh. Do not use the word chemical free, please, because there is no such thing as chemical free. We use chemicals every day. But the new craze is to come up with not so harsh chemicals. And one way to use cleaning products that you make at home, is to use an acid like vinegar and baking soda, which is a base. And so these two can react together and they can help clean a little better. The next characteristics of acids is that they dissolve metals. Depending on the strength of the acid, the stronger the acid, the faster the dissolving will be, the dissolution process. So all acids can dissolve, but they dissolve at different rates. How fast they dissolve depends on how strong the acid is. Let's talk about some common acids, and we already mentioned vinegar. It's called acetic acid. This comes from the Italian word aceto, which means vinegar, and that's why we name it acetic acid. We're very familiar with that. Lemon juice, I already mentioned it, citric acid. Oranges and any citrus fruit, citric acid, they contain the acid, but lemon juice contains it the most, and that's why they taste the most sour. Something you might not be familiar with is aspirin. Aspirin, it contains, the active ingredient in aspirin is acetylsalicylic acid. That is what you take and what actually helps you if you have a headache or if you have a pain, etc., etc. So acetylsalicylic acid in aspirin is what we take to make us feel better. Any carbonated waters, carbonated beverages, if you drink them, they have carbonic acid, H2CO3, dissolved in it, and so we can, that's what you're drinking when you drink carbonated beverages. You drink carbonic acid. These are some of the common acids. Now let's talk about bases. Let's classify the bases. In general, obviously they're going to be the opposite of the acids, but they taste bitter. The acids taste sour, where the bases taste bitter. They neutralize acids, so they react with acids to neutralize them. Once again, I talked about the reaction between vinegar and baking soda. If you've ever done the uh, volcano type experiment for little kids with vinegar and baking soda, you know what I'm talking about. They react, they're neutralizing each other, they're reacting together, and they produce lots of CO2 gas, and that's what you see bubbling. Therefore, they neutralize each other, they react. They feel slippery when you touch them. That's why bases are generally found in homemade soap or soaps in general, and that when you wash your hands with soap, you can feel that slippery feeling, and that's because you're touching bases, and that's what they feel in your hand on your skin. Bases also react with metal ions to produce slightly different products, but they do react with metal ions. And once again, the stronger the base, the faster the reaction with the metal will be, depending on the strength and the concentration, obviously, of either the metal or the acid or the base. Now let's talk about some general common bases that we see in everyday life. Ammonia, a lot of people clean with ammonia, ammonium hydroxide. It's another cleaning agent that we use every day, or not quite every day, but we use commonly in our houses. That is, ammonium hydroxide is a base. Lye is found, or sodium hydroxide is found in soaps, or whether they're liquid or bars, or whether in your shampoos you have some of this in those in general in soaps. So sodium hydroxide is another one, another base. Now, depending on the concentration, sodium hydroxide is a very strong base. But if it's diluted quite a bit, then it's not as harsh, obviously. Milk of magnesia is another one. Here's a picture of it. We take this, it's magnesium hydroxide. You take this if so as an antacid. You have some heartburn, or you can take Tums, for example. Those are made of calcium and magnesium hydroxide or calcium carbonate. What happens is when you take a base, so milk of magnesia, you have magnesium hydroxide as the active ingredient. You take this base and you drink it. Well, what happens is it will hit your stomach. And the reason you have heartburn is because you have an excess of acid, HCl, in your stomach. And the base that you're adding, you're drinking, neutralizes the extra acid, producing water, and it makes your heartburn go away because they got rid of that excess acid. So it's very helpful. That is what all antacids do. They neutralize the acid in your stomach because you're taking a base, and bases neutralize acids. So that's how they help you. Very common, very, very common. Baking soda, sodium bicarbonate, NaHCO3. Baking soda is used widely. It's used in our kitchens as a leavening agent. Most of you, if you've baked anything, you have used baking soda before. And what happens is the baking soda, which is a base, reacts with the acid, typically in a milk or buttermilk, and it forms those bubbles of CO2 gas, and that's what makes your baked goods rise. Depending on how much or how little, it can rise more or less, but that is what's happening, and that's why you get your bread or your muffins or cake to rise, is because of the reaction between an acid and a base. The acid being in milk or in buttermilk, and then the base being baking soda. You can have baking powder, although baking powder contains both an acid and a base in the same powder. But Generally, this is the reaction. You have an acid and a base that's reacting together, and they're producing CO2 gas, which makes your baked goods raise. So that's the general classification of acids and bases. Now let's talk about acids and bases more in a chemical term. There's several different models, but we're going to adopt the Bronsted-Lowry model. First, the model was that the Arrhenius model was that an acid was anything that when was put in water produced H plus ions, and a base, if it was put in water, would produce OH minus ions. Now those cover very specific, a small amount of acids and bases. The Bronsted-Lowry model expands on that to include other acids and bases that do not necessarily release an H plus or OH minus in solution, but still act as an acid or a base. The Bronsted-Lowry model defines acids as those compounds that are H plus donors. They're not limited to aqueous solutions like the Arrhenius model was. H plus donors include compounds like HNO3. We know HNO3 is a strong acid. It releases, it's got a hydrogen here that it can donate, it can give as an H plus, and that's why acids in the Bronsted-Lowry model are defined as those compounds that donate an H plus or a proton. It's the same thing. On the other hand, bases are H plus acceptors. That is what the Bronsted-Lowry model defines bases. They're not, once again, limited to aqueous solutions like the Arrhenius model was. They can accept, so anything that accepts an H plus, a proton, can be a base according to this model. H plus acceptors, it can include ammonia, for example, NH3, the fluoride anion, the OH anion. So you can see that these don't necessarily have to include water. They can just accept the H plus from an acid and they will be classified as a base. That is the general definition. What is the hydronium ion? We're going to talk a lot about the hydronium ion in this chapter. The hydronium ion is just an H plus ion that doesn't have that electron. Remember that that's what the H plus ion is, a proton really, because it's formed from a hydrogen atom losing its electron. It's one electron. And what you have left over is an H plus. It's just one proton because we know that the hydrogen atom has one proton and one electron. If the atom loses that electron, all you have left is one proton. Therefore, the hydronium ion, the H plus, is just a proton that gets transferred from one to the other. Here's an example of that transfer. We have a strong acid here. We have HCl. If we put that in water, what happens is this H plus, so HCl is going to split into an H plus and a Cl minus in solution. And what's going to happen, that H plus is going to be donated to the water to form H3O plus. Basically, I just added a hydrogen to make H3, 3 hydrogen, but also remember that this H has a charge associated with it, so it's an H plus, and that's why the H3O acquires this plus charge. And then what you have left over is the chloride anion, so plus Cl minus. Now notice that on this side, on the left side, on my reactant side, I have no charge. On my product side, my charges have to basically add up to 0 because I have no charges here. If I had a charge here, the charges on the product side would have to equal whatever the charge was on this side. So because my charge on the reactant side is 0, the total charges on the product side would also have to equal 0. I say that in case you forget to add this plus. Then if you did forget it, all you'd have is a minus, which means that your equation wouldn't be balanced because it would have a charge here, a negative charge here, but a 0 over here. So you need a positive charge to balance that negative over here. Now we're going to once again talk a lot about this ion in solution, so you're going to become more familiar with it. But this is a typical reaction that occurs where you have a transfer of that H plus, which makes HCl the ion, or the acid, according to the Bronsted-Lowry model, because it's donating that H plus, and it makes water the base because it's accepting that H plus, and they form H3O plus and Cl minus. Let's look at it in kind of a molecular model. So here's we just talked about it. Hydronium ion is an H plus ion that doesn't have valence electrons. Well, let's see what happens here molecularly. We have a molecule of HCl that is reacting with the molecule of water. This H plus is now transferred to the oxygen over here. So now this molecule acquires a charge because of the plus from the hydrogen. Well, the chlorine that's left is now an ion, and we have a Cl minus. So Cl minus and H3O plus gives me a total charge of 0. And these are the products, and these are my reactants. So this is basically what it looks like when molecularly we're taking this proton. We split the HCl into ions, H plus and Cl minus, and this H plus is being given to the water to form H3O plus, and then we have the Cl minus left behind. This is an important concept because we will be using it quite a bit in this chapter. Now, because we have this transfer of the proton, we will always have what we call conjugate pairs, conjugate acid-base pairs. So in every reaction, acid-base reaction, there will always be an acid-base conjugate pair. Let's talk about what that means. So if this is my reaction where I have HF and I have H2O, I form H3O plus and F minus. Let's talk about, first of all, what is my acid and what is my base according to the Bronsted-Lowry model. Well, if I look over here, I have HF, but over here, my HF is now F minus, which means the HF is the one that gives off that proton. Because it gives that proton away, it's a donor, we call that an acid. So this is my acid. Now, what is left after of the acid, the original acid, after it donates the proton, it's called its conjugate base. Think of these as being, these are pairs, acids and conjugate base together. So what is left over after the acid donates the proton, in this case it's F minus, that is the conjugate base of my acid, the original acid. Do not confuse this one with the base on my reactant side. You will have an acid base as reactant and you have an acid base as product. These are pairs that go together. The clue here is that the acid and its conjugate base will have the same anion. So the F, see this, appears under the acid and the conjugate base. Let's look at the base and the conjugate acid here. We have H2O acting as the base because it's accepting that proton from the fluorine. It's a hydronium ion acceptor, which means it's a base. Whatever forms when the base grabs that proton, that is the conjugate acid of the base that you started out with. So these two are a pair, the base and its conjugate acid, and this is another pair, the acid and its conjugate base. Once again, the conjugate base is what's left after the acid donates the HF, or the H. HF donates the H, you have F minus left. Therefore, these two will be a pair. If this is the acid, this is going to be its conjugate base. The conjugate acid, on the other hand, is what is formed after the base accepts the proton. If this is my original base, after it grabs that proton, it forms H3O+. So this is now the conjugate acid of the base that I started out with. The conjugate base and conjugate acid are those species that appear on the product side, and they are paired with the opposite acid base on the reactant side. What do I mean by that? This is my base on the product side, and it is paired with the acid on the reactant side. Those two are a pair. This is my acid on the reactant or the product side, and it's paired with a base on my reactant side. So these two are an acid-base pair. Therefore, we have two acid-base pairs, the original acid with the conjugate base on the product side, the original base with the conjugate acid on the product side. Let's look at some examples here. If this is my acid, what will be my conjugate base? If this is my acid, I get rid of that H. What's left over is the conjugate base of that acid. So HI, the conjugate base, is I minus. If I have H2SO4 and I get rid of just one hydrogen, H plus, what will I have left? HSO4 minus. I'll have a negative charge here because I got rid of an H plus. H plus plus HSO4 minus should give me H2SO4. If I take HSO4 minus and I get rid of another hydrogen, another H plus, that will lower this charge one more, right? So it goes to SO4 2 minus now because I got rid of another H plus and made this 2 minus. It decreased the charge by 1. If I have CH4 and I get rid of an H plus, that will decrease the number of hydrogens and the charge by 1. So it will make it CH3, 1 hydrogen less, and the charge will decrease from 0, -1, to a -1. Let's look at NaOH. If I get rid of just that hydrogen H plus, I am left with NaO, but it will also decrease the charge from 0, -1, to NaO minus. H3O plus. If I get rid of a hydrogen, that makes 2 hydrogens, but I have a plus charge. If I get rid of a plus, that means it goes to, so I decrease the charge by 1. +1 minus a 1 gives me a 0 charge. NH4 plus, if I get rid of, so obviously these are acting as acids, so they're donating a proton, an H plus. If I get rid of an H plus from NH4 plus, I lower the number of hydrogens by 1, and I have +1 minus a 1 to give me a 0 charge for NH3. So a conjugate base is what is left over after you cut out an H plus from your acid. Let's look at the conjugate acid of the base. So if this is my base, what do I have when I add an H plus to it? Right? Bases are acceptors of H plus. So if I have F minus and I add an H plus, that means that I will have HF. Now I increase the charge by 1 from the to go from bases to its conjugate acid. I have a -1 charge plus a 1 from the proton. It gives me an overall charge of 0. If I have HSO4 minus, it can act as a base by accepting an H plus, which means I add one more hydrogen to make 2. I have -1 plus the 1 from the proton, so -1 plus a 1 gives me an overall charge of 0. If I have H2O and I accept an H plus, that increases to 3 hydrogens, and from 0 plus a 1 gives me +1. Cyanide anion, so Cn minus, if I add a H plus, it becomes HCN because -1 plus a 1 from the proton gives me a 0. NH2 minus, if I add an H plus, I increase that hydrogen to 3. -1 plus a 1 gives me a 0. O2 minus, if I add an H plus, it will become an OH because now I added a hydrogen. Then 2 minus plus a 1 gives me just a -1 charge. CH3COO minus, this is the acetate anion. If I add an H plus, it will give me CH3COOH because I added the H. A -1 plus a 1 gives me 0. So when we go from the acid to figure out the conjugate base, we cut out a hydrogen and we decrease the charge by 1. When we go from the base to figure out the conjugate acid, we add a hydrogen to that base and we increase the charge by 1. This is how we figure out the base and its conjugate acid. Let's look at some examples. Let's talk about the conjugate base of the following acids. So it's telling us that these are acting as acids, which means that they're donating an H plus. So if I start with HCOOH, what I need to do is donate an H plus, so I cut out a hydrogen, and I don't have a charge, which means that when I cut out that proton, I am going to go from 0, decrease by 1, which means I'm going to have a negative charge. The conjugate base of this acid is going to be HCOO minus. So HCOO minus. I cut out that hydrogen and I went from 0 minus a 1 to a -1 charge. Let's look at over this one. I have HPO4 2 minus. It's acting as an acid, which means it's going to get rid of that H plus, increasing the charge, or decreasing, the charge by 1. So it's going to be PO4 3 minus. I got rid of that hydrogen and I decreased the charge. So 2 minus, -1. So -2 minus 1 makes -3. Let's look at HSO3 minus. I get rid of that hydrogen and I decrease -1 by 1, which makes SO3 2 minus. I decreased it by 1, so -1 minus 1 makes -2. Now let's look at the conjugate acid of the bases. I am told these are acting as bases, which means they're going to grab a proton. We're going to add an H plus, which means I'm going to have an H, so HSO4, and increase the charge by 1. So 2 minus plus a 1 gives me a -1. So HSO4 minus. I added a hydrogen, so HSO4, and then I increase the charge from 2 minus plus a 1 to -1. Let's look at this one. CH3NH2. It's acting as a base, so it's going to accept a proton, which means that instead of NH2, I can put a 3, CH3NH3, but I'm also increasing the charge. This has a charge of 0, which means it's going to have a plus charge. CH3NH3, I increased the hydrogens by 1, and I went from 0 plus a 1, giving me a +1 charge. Let's look at pH3. I add a hydrogen, so it's going to make this a 4, and it's going from a 0 plus a 1 from the hydrogen to a pH 4 plus. So here's the conjugate acid of this base. We increased the hydrogen by 1, and we increased the charge by 1. From 0 plus a 1 gives me plus 1. That is just a little bit of practice on how to write conjugate acid-base pairs. It's not that difficult to write them this way, but it's a little more difficult if you actually have the full equation where you have two acid-base pairs. So let's do some practice with those and figure out which ones are acting as bases and which ones are acting as acids. And then the opposite is going to be the conjugate acid, conjugate base for those. Now, not all acids and bases are the same. We know this. We know that we have strong acids and strong bases, and we know that we have weaker acids and bases. We just talked about in a few slides earlier about vinegar, that we actually can eat it in a salad, etc., etc., or the citrus fruit we can eat even though they're acidic. However, depending on the strength, we really can't drink HCl or drink sulfuric acid, H2SO4, etc., etc. That's because they're stronger acids. If we look at the strength of acids and bases, we notice this, that stronger acids are better at donating that H plus than weaker acids. In fact, strong acids, for the most part, dissociate very well. They completely give that hydrogen away and form their conjugate base. Whereas weaker acids, they do not like to give that hydrogen away so much. So very little of that weak acid actually splits to form the conjugate base and donate the H plus. Weak acids, therefore, do not like to donate that H plus. They like to stay in the form of the acid. So if I have, as I said earlier, here, well, this is formic acid. If I had this is a weak acid. It doesn't like to be in this form, so it doesn't like to give that H plus away. It likes to stay as an acid mostly in this form. So very little of it, we say very little of a weak acid ionizes, which means it forms ions, H plus and in this case HCO minus. The strong acids, like going back here a few slides, like HCl, love to give that proton away. So if I put HCl in water, I will not find HCl anymore. I will only find these ions, which means that for a strong acid, this reaction will pretty much go to completion, meaning you will have these products left in solution and you will not have much of this. For a weak acid, it's the opposite. You will have reactants mostly and very little product. So you'll have very little of this H3O plus and that Cl minus, COOH minus, for example. Whereas for strong acids, you will not have much of the reactant left. You will only have product, and the opposite is true for weak acids. The same thing, same idea with a strong acid or strong base. If you have a strong base, you will have pretty much product in solution. If you have a weak base, you will have pretty much reactant in solution and not the product. That's because they don't ionize very well. So strong bases are better at accepting H plus ions than weak bases. So they grab that proton very easily to form the conjugate acid. Stronger acids have weaker conjugate bases. So if I'm looking at a strong acid conjugate base pair, the strong acid is much, much stronger than its conjugate base. And the opposite is true for the weaker acids and bases, obviously. So here's a table where I have acids listed and bases. And you see that I have acid-base pairs over here. If this is perchloric acid, this is its conjugate base. This is my acid, this is conjugate base. So you can see the pairs. This is sulfuric acid, this is its conjugate base. This is my base, this is its conjugate acid, depending on which direction you're going. But notice that the strength, as the acid strength increases, the base, the conjugate base strength decreases, right? So if I'm going up here in the same direction, as the acid strength increases, the strength of its conjugate base decreases as I'm going in the same direction. So they increase in opposite directions, which is this point over here. Strong acids have weaker conjugate bases. The stronger the acid, the weaker its conjugate base means. What does that mean? Let's look at practically. Let's pick sulfuric acid because we're familiar with these acids. It's a strong acid, which means that because it's a strong acid, it fully ionizes in water. It completely splits apart to an H plus and HSO4 minus. This is its conjugate base. Because it's a strong acid, it completely dissolves or dissociates to form this and the hydronium ion, which means that if I put this in water, I don't have H2SO4 anymore. I will have HSO4 minus because it's a strong acid. Let's look at the base. HSO4 minus, it's a weak base compared to the acid because it likes to stay in this form. It does not want to grab that proton to go back to H2SO4. It likes to stay as HSO4 minus, which means that it's a very weak base. By a strong and a weak, we're defining how much do they like to react with either to accept a proton or to give away a proton. Let's look on the other spectrum over here. Let's look at ammonia because we're familiar with it. Ammonia is a very weak acid, does not undergo much dissociation in water. It doesn't split into ions. It doesn't give off that H plus. So if I have ammonia in water, I mostly will have NH3. Now let's look at NH2 minus, the amide ion. NH2 minus is a very strong base because it does not like to stay in this form. It wants to form the acid. So NH4 minus reacts very, very well. It accepts a proton very easily to get to the acid, and it stays that way. It likes to stay as the acid and not the base. So you have these strong acid, weak acid, strong bases, strong acid, weak base pairs in solution. And in general, the stronger the acid, the weaker the base. As the strength of the acid increases, the strength of the base decreases. And this is for acid-base pairs. This is a list of 6 of the strong acids and strong bases, which means that if I'm talking, let's say, about perchloric acid or hydrochloric acid, hydrobromic, etc. So these acids in solution fully ionized. They do not appear in this form when you put them in water, because they completely give off that H plus, and they appear as their conjugate base. Because the perchloric acid is so strong, its conjugate base, ClO4 minus, is a very weak base. It does not accept that proton very easily. The same with all of these acids, because they're strong bases, their conjugate, or I'm sorry, because they're strong acids, their conjugate bases are very weak. The opposite is true for these. These are the 6 strong bases that we talk about, and they completely ionize in solution. And because they do that, their conjugate acids are very, very weak. They do not like to accept that proton, or the acids are weak, which means they don't like to give off the proton very easily. So that's the strength, the relative strength of acids and bases. Remember, if the acid is strong, its conjugate base that is formed after the acid drops that H plus is going to be a very weak base, meaning it doesn't like to accept the proton back. If you have a strong base, which means that it accepts a proton very easily, you have the conjugate acid that is formed is very weak. It does not like to give that proton away. That's the relative strength of acids and bases. How do we determine, so we know that there's a relative strength of acids and bases. How can we tell then which acid is stronger and which acid is weaker, or base and stronger or weaker? We do that by what we call acid-base dissociation constants. These are equilibrium constants, just like the ones that we talked about in chapter 13, but we call them acid-base dissociation constants, or your book likes to call them ionization constants, and they are the same, they have the same idea as an equilibrium constant, and they're written the same exact way as an equilibrium constant. Let's take an example for an acid. This is vinegar. This is acetic acid. If we put it in water, notice that water is the solvent, so it appears as a liquid. We know that it's an acid, so it's going to donate the H plus to the water to form its conjugate base, CH3CO minus, right? If I get rid of an H plus, what I have left is cross this hydrogen out. I have this left, but with a minus charge because this is a 0, and I decrease it by 1 because I got rid of that proton, CH3CO minus, and the base, water here is acting as a base. It accepts this proton to give me the conjugate acid of water, which is H3O plus. If I write this equilibrium expression for acids and bases, they're called Ka for acid and Kb for base. The dissociation constant for the acid is written the same way as the equilibrium constant that we talked about in chapter 13. This is a specific class because it deals with acids and bases. So Ka is going to be the concentration, molar concentration of the H3O plus ion multiplied by the molar concentration of CH3CO minus ion divided by the concentration of your acid. Notice that the water doesn't appear because it's a liquid. This is how you write equilibrium constant expressions, dissociation constants for acids, and then we'll get to the base here in a little bit. But you have molar concentrations of your products multiplied, divided by the molar concentration of your reactants. Notice that because it's a 1-to-1 ratio, I don't have any any powers here other than 1. And typically, because we transfer a hydrogen 1 at a time, they're all going to be to the first power. Now we can have Ka values that are very large or very small. And recall from chapter 13 that we said if K is very, very small, that means that this top number is very small, which means that the bottom number is large, which means that the acid doesn't like to dissociate or split to give off that ion, that H plus, very easily. So you'll have very little product and a lot of reactant for a small Ka. If you have a large Ka, that means the top number is much, much larger than the bottom number, which means you have a lot more product than you have reactant. These are for very strong acids. You have very, very large Ka values, which means they completely ionize, they completely dissociate into these ions. So you have product and very little, if any, reactant. For weak acids like vinegar, acetic acid, you have either a moderate, so 10 to the minus 5, or these are very, very weak if you go to the minus 10, very weak acids. And we talked about why that is. So you have a small number divided by a large number give you a small Ka. That means that the only way to have that is if you have much, much more reactant than you have products. Let's talk about the bases. It's the same concept. We write, if this NH3 is acting as a base in water, it accepts a proton from the water. Notice that now the water is acting as the acid by donating a proton to NH3 to form NH4+. I increase by 1 because it's accepting an H+, and I also increase the charge by 1 from 0 plus 1 to plus. And here I cut down the number of hydrogens because it's giving 1 away, and I go from a 0 and I decrease by 1, so OH minus 1 because I went from 0 minus a 1 to minus 1. How do I write an equilibrium constant or a dissociation constant for the base? I have molar concentrations of my products, so NH4 plus multiplied by the molar concentration of OH minus divided by the concentration of NH3. Notice that we're talking about molar concentrations now because we are in solution. We don't deal with gases when it comes to acid-base reactions, and therefore we're only going to talk about molar concentrations. The same idea as a Ka is applied to Kb values. If I have a large Kb value, that means that my top number is much, much bigger than the bottom, which means I have pretty much product and very little reactant, which means I have a very strong base that likes to completely split apart or dissociate into solution. The opposite is true for a very, very small Kb. If I have a small Kb value, that means my top number is very small compared to the bottom number, which means, as in this case, for NH3, I have a very weak base. It likes to stay this way. It does not like to split up into ions. That is how we can tell if we're comparing two acids or two bases, that is how we can tell which one is the stronger, which one is the weaker. A stronger acid will have a larger Ka. A stronger base will have a larger Kb value. A weaker acid has a larger Ka. A weaker base has a larger Kb. We also talk about percent ionization. It's the same idea as the percent by mass that we had done previous chapters. What we're comparing is the concentration of, for the acid, for example, the concentration of H3O plus that is formed divided by the initial concentration of my acid, HA stands for the acid, so the concentration of H plus or H3O plus in solution, divided by the initial concentration of my acid, multiplied by 100. The same idea with a base. But instead of H3O plus, I'm looking at OH minus. What is the concentration of OH minus? Divided by the initial concentration of the base in solution times 100. The larger the H3O plus or OH minus concentration, the larger the percent ionization, obviously. So the larger this number and the larger that number, the larger the percent ionization, which means the stronger the acid of the base. A strong acid will produce more of H3O plus ions than a weaker acid. Therefore, its percent ionization will be larger. The stronger base will produce more of these OH minus ions in solution than a weaker base. Therefore, its percent ionization will be larger if the initial concentrations are the same for both acids. That is how we can tell which acid or base is stronger, either by looking at the Ka values or the percent ionization values. It's the same idea. Let's look at some examples on how to write Ka expression. First, how to write an equation, how to write the Ka expressions as the weak acids. And it tells us that these are acting as weak acids, which means that this, if I put this in water, is going to donate that H plus, and we get a minus charge. So here's the chemical equation. So if I have my acid and I put it in water, I cross out that H plus because it goes to the water. So I'll have OClO left over, but I also decrease the charge by 1. So I go from 0 to a minus 1. And I have H3O plus over here because water is acting as a base. It's accepting that proton. I increase the number of hydrogens by 1 to go to H3. And I also increase the charge by 1 to H3O plus. How do I write a Ka expression? Molar concentrations, so the product of the molar concentrations of my products over my reactants. Here's the Ka expression for this acid. H3O plus, molar concentration, times the molar concentration of OClO minus, divided by the concentration of my acid, HOClO. Let's look at the monohydrogen phosphate ion, HPO42 minus. It's acting as the acid, which means it's going to get rid of the H plus. Here's the reaction, HPO42 minus plus a water, which is acting as the acceptor, the base, giving me H3O plus. It's accepting the H plus, so H3 and plus increases in charge. PO43 minus, because I got rid of that H, and I decrease the charge by 1. The Ka value then becomes the molar concentration of H3O plus times the molar concentration of PO3 minus divided by the molar concentration of HPO42 minus. Let's look at HBRO3. HBRO3 plus water, this donates that proton to water, so I have H3O plus BRO3 minus, I get rid of the H and I decrease the charge by 1. The Ka value then is the molar concentrations of my products multiplied, divided by the molar concentration of my initial acid. So H3O plus concentration times BRO3 minus concentration divided by the HBRO3 concentration. Notice that in none of these does the water appear because it's a liquid, and we talked in chapter 13 how we don't write the concentrations of the liquids or solids in these types of expressions. So that's why I don't have H2O down here. Let's look at The Kb expressions do the same thing but for these bases. Now I know that they're acting as bases, so they're going to accept a proton, which means I'm going to increase the H concentration and the charge by 1. So here's that reaction. I have N2H4 plus water. The water now is acting as the acid. It's giving that proton to the base. So I have N2H plus H5. I increase that 4 to a 5 because I'm adding a proton. And I increase the charge from 0 to plus 1. So N2H5 plus my water is decreasing in protons. So I decrease the hydrogen by 1. I also decrease the charge by 1. From a 0 minus a 1 gives me a minus 1. So this is the reaction. The same thing for writing a Kb expression is the molar concentration of my products multiplied, divided by the concentration of my base, and H2O doesn't appear. So here's N2H5 plus concentration multiplied by OH minus concentration divided by N2H4, which is the concentration of my base initially. Let's look at the bicarbonate ion. It's acting as the base. It's accepting a proton. So I will increase the hydrogens to 2. I will also increase the charge minus 1 plus a 1 to a 0. Here it is. HCO3 minus plus an H plus from the water gives me H2CO3 with a 0 charge because a minus 1 plus a 1 gives me 0. And the water, losing a proton, goes to an OH minus. To write the Kb expression, I multiply the molar concentrations of H2CO3 and OH minus, and I divide it by the concentration of HCO3 minus. Notice that the water doesn't appear. The benzoate ion will act as a base, will accept a proton, so we'll add a hydrogen, and this goes from minus 1 plus a 1 to 0. Here it is. Here's my benzoate ion. It becomes benzoic acid, C6H5COOH. I added a hydrogen, so here I have written the O's out. Here's O2, but it's the same idea. The hydrogen I added, and I went from a minus 1 to a 0 charge because minus 1 plus a 1 from the hydrogen gives me 0. And water, when it loses a proton, becomes the OH, and this has to be aqueous as well. And the Kb is written the same way as I wrote these. The concentration, molar concentration of my benzoic acid multiplied by the concentration of OH minus divided by the concentration of the benzoate ion. This is the way that we write acid and base reactions in water and how we write Ka and Kb values. I am going to stop here for part 1 of the lecture and then continue with the auto-ionization of water in part 2 so that the files do not become so large when I put them on YouTube.